Hello, this is John Miares, and in this lesson, we're going to be looking at the properties of arithmetic and geometric sequences. We introduced sequences in general in section 12.1, and we did identify a few that we said would look more closely at in these two sections. Because these sequences have certain patterns to them, the implicit and explicit formulas for evaluating arithmetic and geometric sequences, and to a lesser extent their certain partial sums, can be generalized. Now, these sections are both pretty short, so I've combined them into a single lecture for simplicity's sake. But there will be two separate problem challenges, one for each section, that I'll be asking you to complete at the end of the lesson. What is an arithmetic sequence? A sequence is considered arithmetic if there exists a number, usually labeled with the letter D, called the common difference, such that when we look at the sequence implicitly, the nth term of the sequence will be the value of the previous term plus D. Now, there's nothing to say that D has to be a positive number. It could be a negative number, in which case we're subtracting a common value from one term to the next every time. If we wanted to create an explicit formula, we could write a sub n equals a sub 1 plus d times n minus 1. Here we have a couple of sequences that we worked on in section 12.1 that were defined as arithmetic. The first one has a common difference of 3, and the second one has a common difference of 2. Let's look at a different example. Suppose I have this sequence that starts at -8, then goes up to -5, -2, 1, 4, and so on. Suppose you were asked to find the first term and the common difference so that we can apply the general formula for arithmetic sequences. After that, suppose you were asked to find the 12th term of the sequence and then asked to find what term in the sequence will get you the number 85. Now, we could probably do this by what I call the brute force method, where we see the pattern and just keep adding by the common difference until we get to the 12th term or until we get to the number 85. But I'd like to see how we can look at this generic formula and how it applies. The questions in the first bullet here are easy to answer. The first element of the sequence is -8, and the common difference is 3 since we're adding 3 every time to get from one term to the next. If we look at the formula for an arithmetic sequence where a sub n equals a sub 1 plus d times the quantity n minus 1, we can plug in what we see here and get that a sub 1 is -8, d is 3 in this expression, and simplifying the result. Distributing the 3, we get -8 plus 3n minus 3, which simplifies to 3n minus 11. This is our simplified explicit formula for this arithmetic sequence. To get the 12th term of the sequence, we can now plug in 12 for n and get 3 times 12 minus 11. 3 times 12 is 36, which when you take away 11 gives 25. Now for the third part of the problem. We want to know which term in the sequence gives 85. What that means is I will set the formula that represents the sequence equal to 85 and try to solve for the value of n. So 3n minus 11 equals 85. Moving the 11 to the other side, we get 3n equals 96, which when we divide both sides by 3 leaves us with n equals 32. This means that the 32nd term in the sequence, or a sub 32, will equal 85. Here's a similar example. Suppose a sub n is an arithmetic sequence where a sub 1 equals 14 and the common difference d equals 3. Write the expression for a sub n, then determine the value of a sub 20. Just like before, we're going to start with our generic formula a sub n equals a sub 1 plus d times the quantity n minus 1. We're given that a sub 1 equals 14 and that d equals 3. Substituting those values into the formula, we get a sub n equals 14 plus 3 times the quantity n minus 1. Distributing the 3 through those parentheses gives 14 plus 3n minus 3, which simplifies as 3n plus 11. So to get to the nth term, we're going to take our index value n, multiply it by 3, and add 11. To get to the 20th term, we just substitute n equals 20 into the formula to get 3 times 20 plus 11, which will simplify to 71. This example is a little trickier. Suppose a sub n is an arithmetic sequence with common difference d, where a sub 1 is 8 and a sub 11 is 26. Determine the value of d, then write an expression for a sub n. We have our formula for the arithmetic sequence, and we are given a sub 1, but we're not given d. Instead, we're given a sub 11, which is the 11th term in the sequence. The question becomes, what can we do with that information? Well, we could treat 11 as n and substitute the 26 in for a sub n in the equation. Then we already know a sub 1 equals 8 and n is 11. We can now use this information to find the common difference. Simplifying inside the parentheses, this equation becomes 26 equals 8 plus 10d, which when we move the 8 to the other side becomes 10d equals 18, or d equals 1.8. Now, you might be looking at this and wondering whether you did something wrong because your answer came out as a decimal. Nope, this is correct. You're in college now. Not every problem comes out with a whole number answer. Knowing that d equals 1.8 and a sub 1 equals 8, we can plug those knowns into our expression to get a sub n equals 8 plus 1.8 times the quantity n minus 1. Now you do have the option of simplifying this expression into 1.8n plus 6.2, but that is not required. Some of the problems on the homework ask you to identify whether or not a sequence is arithmetic. Let's look at a few of these. In one, our sequence starts at 100 and goes to 68, 36, 4, and so on. Is this one an arithmetic sequence? The answer is yes. There is a common difference between the numbers that will get you from one term to the next. We're always subtracting 32, so we could think of that as having a common difference of negative 32. If we wanted to apply the formula, we could write this as a sub n equals 100 plus negative 32 times the quantity n minus 1. If we distribute and simplify this equation, which is not necessarily required, it would become a sub n equals 132 minus 32n. Here's another example. This is a sequence of fractions starting at 1/2 and continuing on to 1/3, 1/4, 1/5, 1/6, and so on. Is this an arithmetic sequence? The answer is no, because there is no common difference associated with this problem. There is a common difference in the denominator of the fractions, but when you look at the overall value of the fractions themselves after taking 1 over each value, you see that it's not going to be arithmetic because the difference between each term isn't consistent. How about in this third example? The answer is no, because again, there is not a common difference. The sum of the logarithms will actually be the product of the individual numbers you're taking the log of. You can probably verify this easily enough with a calculator so that if you decimalize the values of the natural logs of 2, 4, 6, and 8, you can pretty quickly see there isn't going to be a common difference here. Now that we've talked about the general form of an arithmetic sequence, we can start talking about partial sums of arithmetic series. As you might recall, the nth partial sum of a series is the sum of the first n terms of that series. Our formula, S sub n, is going to be given as you see here, n over 2 times the quantity a sub 1 plus a sub n. Now, this is not an intuitive formula, so we're going to look at a regular example and see how it applies, which will hopefully make the formula make that much more sense. Suppose you wanted to find the sum of the first 100 natural numbers and you didn't want to add them all up in your calculator one at a time. There is a shortcut that we can use to approach this problem. Let's look at the first and last numbers. If you add these together, 1 plus 100, you get 101. Now let's look at the second number and the second to last number, 2 and 99. These also add up to 101. If we look at the third number and the third from the last number, 3 plus 98 again gives 101. Continuing, you could take 4 plus 97 and again get 101. Hopefully what you're seeing here is that we can continue this pattern for every pair of numbers as we work towards the middle of the list, and we're going to keep adding 101 and 101 and 101 over and over and over again. What you should also notice is that because we're grabbing two numbers at a time, we're adding the number 101 over and over again 50 times because there are 50 pairs of numbers in that list of 100 that can be added together to give us 101. Combining that together gives us 50 times 101, which adds up to 5,050. Now that we've seen this process work intuitively, let's see how it works when we apply the formula. So we have a sub n equals a sub 1 plus d times the quantity n minus 1. We can see that a sub 1 equals 1, and based on the pattern, we see that we have a common difference of 1. There are 100 numbers in this sequence with a common difference of 1, so a sub 100 will equal 100. Looking at our summation formula, we have n over 2 times the sum of a sub 1 and a sub n. Plugging in n equals 100, a sub 1 equals 1, and a sub 100 equals 100, this will simplify to 50 times 101, which equals 5,050, the same answer we had before. So in essence, the a sub 1 and the a sub n added together are like when we added the first and last terms together when we were doing the problem by hand. The n over 2 is when we realize that there are that many pairs of numbers that we're adding together. Here's the next example. Suppose we're asked for the 20th partial sum here, where a sub 1 equals 14 and d equals negative 3. We have our formula for the nth partial sum, n over 2 times the quantity a sub 1 plus a sub n. We know n is 20, so we can plug that in to get 20 over 2 times the sum of the first term and the 20th term. We also know the first term, a sub 1 equals 14, but we don't know the 20th term, so we're going to have to evaluate it. Let's start with the formula for an arithmetic sequence. A sub n equals a sub 1 plus d times the quantity n minus 1. We're given a sub 1 equals 14 and d equals -3. So subbing that in gives 14 plus -3 times the quantity n minus 1. We can distribute and simplify to get a sub n equals -3n plus 17. Knowing we want the 20th term, we can substitute in 20 for n and get -60 plus 17, which simplifies to -43. Now we can go back and fill in our information to get the 20th partial sum. So S sub 20 is going to be 10, the 20 over 2, times the quantity 14, which is A sub 1, plus -43, which is A sub 20. Simplifying inside the parentheses gives -29, and 10 times -29 is -290. So that tells me that S sub 20, the 20th partial sum of the series, the sum of the first 20 terms of the sequence, is -290. If you don't trust that, you can always try to evaluate it the long way, because what's happening here is as we move our way forward in this sequence, we're getting negative numbers that are getting further and further from zero. So as we add them up, the number we end up with is a number whose absolute value is quite large, but whose overall value will be negative. We can also use this formula to evaluate sums of arithmetic sequences that are written in sigma notation. Here's an example. Here we're asked to find the value of the sum from k equals 5 going up to k equals 20 of the expression 8k. Now, some of you may be asking, how am I supposed to evaluate this if I'm not even given the first term? We're given the fifth term and the 20th term. Well, that doesn't mean we can't manipulate the circumstances to fit our situation. Here's our S sub n equals n over 2 times the quantity a sub 1 plus a sub n formula. In order to rethink this, let's put this formula into plain English. What the formula is essentially saying is that the sum of the nth partial series will be the number of numbers in the sequence divided by 2 multiplied by the sum of the first and last number in the sequence. Even though we're starting at k equals 5, this is still an arithmetic sequence, so we can just think of the result as plugging in k equals 5 as our first number that we'll use to evaluate a sub n. So we're going from k equals 5 to k equals 20. We have 16 numbers that we're working with. So I'm going to enter n equals 16. The first number in the sequence, as we have it, will be 8 times 5, which is 40, and the last number will be 8 times 20, which will be 160. Combining those together will give us 200 inside the parentheses. After we multiply by 8, this gives us a total of 1600. So the sum of the expression 8k going from k equals 5 to k equals 20 will be 1600. All right, that's enough for section 12.2. I think we're ready to move on to section 12.3 and geometric sequences. A sequence is considered geometric if there exists a number r called the common ratio such that a sub n plus 1 divided by a sub n equals r, or the next term a sub n plus 1 equals a sub n times r for any integer greater than or equal to 1. The nth term of a geometric sequence can be given explicitly by the formula a sub n equals a sub 1 times r to the n minus 1 power, where n is greater than or equal to 1. Here are a couple of examples of geometric sequences we've worked with already. In the first one, the common ratio is 2, and in the second one, the common ratio was -3. Here's our first geometric sequence example. Suppose we're given the geometric sequence implied by the following pattern: 625, 125, 25, 5, and so on. We're asked to find the common ratio, then the eighth term of the sequence, and then a formula for the general term or the nth term. To find the common ratio, we need to figure out what each term in the sequence is getting multiplied by to get to the next term. We have a sub 1 equals 625, and to get to 125, we would normally have to divide by 5. Similarly, going from 125 down to 25 means dividing by 5 again. Then 25 divided by 5 is 5, and 5 divided by 5 could continue along in our sequence. What it looks like here, though, then, is that I'm not multiplying by a common factor, but actually dividing by 1, which, yes, I can see people getting confused and asking themselves, is this even a geometric sequence, or is it something different if I'm dividing by a common factor instead of multiplying by 1? Here's what we have to remember. Just like when we were dealing with decreasing sequences in the last unit, it is possible to have a geometric sequence decrease like this one. We just need to rethink our approach to it. If we normally divide by 5 to get to the next term in the sequence, the equivalent of that would be to multiply both sides of the expression by 1/5. Subbing in what we know into our general form of the geometric sequence, we can get a sub n equals 625 multiplied by 1/5 raised to the n minus 1 power. To get to the eighth term of the sequence, we take 625, our first term, and multiply by 1/5 to the seventh power. So we're getting 1/5 by 1/5 by 1/5 done 7 times after our first term to get to the eighth term, which, if we use our calculators, you will see comes out to 1/125th. We could also do this by brute force and just follow the pattern you see until we get to the eighth term. As you can see, you're dividing by 5 or multiplying by 1/5 to get from one term to the next. So if you continue this pattern, we get 1, then 1/5, then 1/25th, and finally 1/125th to get our eighth term of the sequence. Here's another example. This one's a little trickier because we don't have the first term or the common ratio. Suppose the fourth term of the geometric sequence is -2 and the seventh term is 1/4. We want to find the common ratio and write an expression for a sub n. To visualize this a little bit better, perhaps the brute force method isn't a bad way to start. I'm given the fourth term and the seventh term in this expression, so I'm going to put 7 blanks in here representing the first 7 elements of my sequence and see what happens. We're given that the fourth term is -2 and the seventh term is 1/4. In between, we know that the sequence is geometric, and so we're multiplying by a common ratio in order to get from one term to the next. So to get from the fourth term to the fifth term, we have to multiply by r. Then to get to the sixth term, we multiply by r again, and to the seventh term, we multiply by r one more time. This gives us -2 times r times r times r equals 1/4. Now, before we panic, we have to realize that repeated multiplication of the variable r can turn into an exponent. So we can simplify this as -2 times r to the third power is 1/4. Dividing both sides by -2 gives r cubed equals -1/8. After we take the cube root of both sides, this is simplify to r equals -1/2. Now let's use that information to fill in some of our blanks above. If r equals negative 1/2, then the fifth term of our sequence is going to be negative 2 times negative 1/2, which simplifies to plain old 1. Multiplying that by negative 1/2 gives negative 1/2, which in turn, if you multiply by negative 1/2 again, will give you positive 1/4. Now, we still have to work our way backwards towards the first term, and while we can use algebra on this one, it might be easier just to work backwards in the pattern. If we're multiplying by negative 1/2 to move forward in the sequence, we're going to have to divide by negative 1/2 to go backwards in the sequence. Dividing by negative 1/2 is the same as multiplying by negative 2, so the third term in this sequence is going to be 4. Continuing this pattern will get us a sub 3 equals negative 8 and a sub 1 equals 16. So now we know our first term is 16 and our common ratio is negative 1/2. So our final answer for the geometric sequence can be written as a sub n equals 16 times negative 1/2 to the n minus 1 power. There's also a formula that can be used to find the nth partial sum of a geometric series. That formula is given here, where S sub n equals a sub 1, the first term, times the quantity 1 minus r to the nth power, all divided by 1 minus r, which will work so long as r does not equal 1. Let's look at this example here. Find the sum of the first 8 terms of the geometric sequence from example 1. For those who don't remember and don't want to rewind the video, the sequence is given as a sub n equals 625 times 1/5 to the n minus 1 power. This means that a sub 1 equals 625 and r equals 1/5. Applying this formula here, we can substitute in r equals 1/5 into both places, and n equals 8, and a sub 1 equals 625. From there, we can very carefully use our calculator to evaluate each piece of this expression, which can then divide out to simplify as 781.248. Here's another example. Let's try the same thing for example 2. In example 2, we had 16 times negative 1/2 to the n minus 1 power. From this, we get a sub 1 equals 16 and r equals negative 1/2. Since I want to know the sum of the first 10 terms, I can substitute n equals 10 into the formula and r equals negative 1/2 as we see here. Evaluating each piece carefully and then substituting in a sub 1 equals 16, the result should simplify to 10.65625. Now, one thing that is possible under certain circumstances is that we can compute the sum of an infinitely long geometric series provided that the common ratio is something between negative 1 and 1. In this way, each successive term is getting smaller than the one before it, so that when you add up all the terms, eventually the numbers you're adding to the sum are all so small that they become inconsequential to the entire total. If the absolute value of r is less than 1, then the limit or the sum of an infinite geometric series is given by the formula s equals a sub 1, our first term, over 1 minus r, the common ratio. Now, if the absolute value of the r is greater than or equal to 1, then the sum of the series is going to be divergent, meaning that the sum is going to increase without bound to infinity or possibly negative infinity, since you will keep adding numbers that are bigger and bigger in absolute value to your totals. To see this formula in action, we're going to look at the two examples we've worked with already in this section and see what the sum of the infinite geometric series looks like. From example 1, we had a geometric series whose first term was 625 and whose common ratio was 1/5. If we look at this formula, the sum can be computed by subbing in a sub 1 and r, giving 625 divided by the quantity 1 minus 1/5. The denominator will simplify to zero point 0.8, and 625 divided by zero point 0.8 becomes 3,125 over 4, or 781.25. Now, if you remember from earlier, the sum of the first 8 terms of the sequence was 781.248. So you're now adding an infinite number of terms together, but didn't really increase the overall value of the sum that much after looking at the first 8 terms. That's mostly because the r value we're using here is pretty small. From example 2, we had a geometric series with the first term being 16 and the common ratio being negative 1/2. Substituting those values into this formula gives 16 divided by 1 minus negative 1/2. The denominator, when you work out the double negatives, becomes 1.5, so the fraction will reduce to 32 thirds, which as a decimal becomes 10.66666 repeating, or again, 10 and 2/3. When comparing the sum of the first 10 terms of the sequence, remember, the sum of the infinite terms, again, really wasn't that much bigger. It's important to remind you that this formula is, of course, going to only work when the common ratio r is a value between negative 1 and 1. While you can evaluate the formula and get an answer for s when the absolute value of r is 1 or greater, it actually doesn't give you the sum. When your common ratio is 1 or greater, the terms in the sum keep getting bigger and bigger and bigger, and the sum will increase without bound. Similarly, you can never have a clean formula for the sum of an infinitely long arithmetic series for the same reason, because the numbers we keep adding are going to get bigger and bigger and bigger, and the sum will eventually just diverge to either infinity or negative infinity. The only way this works for a geometric series is that the terms you're adding keep getting smaller and smaller and smaller to the point where eventually you're not adding anything more. Imagine if I asked you to walk towards the wall you're standing closest to, but only go halfway to the wall and stop. Then, if I asked you to go half the distance to the wall from where you are now and stop, and then half the distance again and stop, and again, while you're cutting the distance you are from the wall by half every time, you end up technically never actually making it all the way to the wall because there will always be a small distance that will be in between you and the wall that you can cut in half. Here's the problem challenges for section 12.2 and 12.3. Yes, it is two problem challenges, but these problems tend to go very quickly, so they shouldn't take you too long to complete both of them. The answers to all of these should be in the back of the book, and I do plan on going over these in an upcoming ORT session. But if you have questions ahead of time, you know what to do. You've got my email, you've got the discussion board. Thanks for watching, and we'll see you all soon.